Welcome to CS235, and this is lecture 11. I'm going to start out with a few administrative items. So real quick, first I'm going to hand out the Clark keycard access forms. Actually what I'm going to do is I'm going to put a stack around, and you're all welcome to circulate them. So find your name. They're not in alphabetical order because that would have taken time. So I sent you all an email previously giving you very detailed instructions, including a picture walkthrough of where to go to get your card. So take this form and a photo ID, so either your student Stanford ID and or your driver's license, to the office in those instructions. If you can't find the instructions, just search your Google for the email I sent, and it should be fairly self-explanatory, and this will allow you to use the restroom. Now, in a much easier bout of administrative battles, Gates just said, oh, thanks for the list of students, come over and get your key. So, you also need keys to the Gates building, because that's where we're going to be building our final projects. So, it's on the first floor, and if any of you have been on the first floor of Gates, there's the fishbowl, the AI lab, and then the not that. So you want to go to the not the fishbowl. So it's where all the administrative people are. And if you were to walk over from Clark right now, it would be the closest door to you in a straight line. And the woman's name is Christine Fixtel. Her helper is Hector. Either one of them can help you. They'll just want to see your ID. Your name will be on the list I gave them. They'll give you a key. One quick note about Gates keys. For some reason, they can't figure out how to have computerized keys in the computer science department that work. So if you want access to a door, you take your key and you stick it into the door until it beeps. After a few, I think you have 24 hours in which to do that to every door you want access to. Do it to the elevator. Do it to all of the external doors. If you don't do that within 24 hours, your key will not work for any of the doors you did not stick it in and hear the beep.
I think it's a month.
Huh?
I think it's a month.
They told me 24 hours. They might be pulling my leg. So for our purposes, so we don't have to do it again, make it 24 hours. Remember, every door you want to be able to use, the key has to go into within 24 hours.
Why do we need access to Gates?
That's where we're going to be building final projects.
What room is it?
Huh?
What room in Gates?
The 2A cube cluster, we'll talk about that another day. Okay, I need you all to be in groups of 3 by Wednesday. And once you are in said group, please email me the details. If you are planning to do a special research project, I need to actually talk with you one-on-one to approve that. And we need to do that by end of lecture Wednesday. Keith, I have gears for you. Jonathan, I have gears for you.
Thank you.
For Gates, do we need any form?
Nope. All you need is your ID, and I already.
We need a deposit.
Oh yeah, and $20. I forgot about that. Thank you. And $20. But if you bring the key back, you get your $20 back. And the keys are good through June 14th, the day after grades are submitted. Okay, just a few quick notes. Today's going to be a bit faster. If you have a burning question, feel free to ask it. If you have a question that could probably wait until the end, it would be a service to everyone to do that. Just a few notes from watching people with Lab 2. So Lab 1, the annoying thing was shafts, right? Among other things. For Lab 2, the annoying thing was shims. So everyone had a nice fat stack of 0.5 millimeter shims. Does anyone know how to not have to do that ever again? Order them from Masumi. So Masumi has shims, and depending on which ones you get, you can have increments of 0.01 millimeters is the delta. So you could have it 1 or 1.01 or 1.02, and I don't know about that. I know for sure they have increments of 0.1 because I use them constantly. So then instead of having a 6 millimeter or 12.5 millimeter shims to do 6 millimeters, we would have one 6 millimeter shim, and the part count drops precipitously. So this is another one of those things where A, we didn't have time or money to get them from Masumi, but B, I wanted you all to have a little bit of a burn from the lab just so that you understood why this is so important. So I haven't used little shims for stacks in years. I just always get them from Masumi. But now you know why, because it's almost impossible to install and you need tape and tricks. Okay, so you were all dutiful in reaming the little knobs and the pulley assemblies, and that was great. But most of you discovered that they were still tight. The reason for this is in soft materials, there's something, well, in all materials, but particularly in soft materials, there's something called springback, which is basically when you're cutting the material, some of the material doesn't get cut away. It simply elastically deforms out of the way. And then once you remove the cutting tool, the material, quote, springs back. And so then that's why you'll notice you reamed it and it got better but not perfect. So typically you'll just ream it 2 or 3 times. Ream it, take it out, blow off the dust, ream it again, take it out, do the same thing 2 or 3 times. And you know, this is why if any of you have ever used a lathe or a mill, you don't just do one pass with the cutting tool and then that's it. You then go back and then you go back again. Going back again gets that last little bit of material that, let's look at it this way. If I'm trying to cut, if I'm trying to take this chunk of material here and then cut down here, if I zoom in a different color, I'll have just a little bit that got left over. And some of it will be because either the tool bent and went out of the way, and part of it, particularly in our case, is the material bent out of the way and then came back after we removed the reamer. So the second pass gets rid of that. Okay. Some of you used screws that were the incorrect screws. So the ones for the rollerblade wheels were button head, and their profile was this. Some of you used ones like this. What's the problem with these, potentially? They stick out too much. So I think you guys got lucky. I probably should have designed it so it wouldn't have worked, but the bearing flange was right about here, and I gave you lots of clearance with the button head. That's why I used those screws. And here you could have either gotten lucky or not lucky, and it would have jammed up and prevented rotation. Anytime you're assembling something, I want you to look at your CAD. The CAD is open. You're looking at every single part and verifying. If you have 2 or 3 parts, it's not such a big deal, but even by lab 2, we had people using the wrong dowels and the wrong screws, and you only barely got lucky. Now, if this were metal and you didn't get lucky and you ruined your parts, then that would be very bad. So asking the guy next to you or the girl next to you what screw you should use is not adequate, because they might not know. Asking the machinist who's working on your part is not adequate, because they definitely don't know. So you need to have your CAD open. Okay, another thing is calipers. Yesterday we had, I don't know, 8 or 10 people in the back room and not a single set of calipers. Now, I'm not blaming all of you. I haven't thoroughly indoctrinated yet. You should never be assembling anything without a nice set of calipers sitting right next to you. Because if you're using shims and you're not measuring to verify their thickness, that means that you're going to have some error like this. I always want to see people assembling with calipers and measuring things as they put it in the robot, because in my dissertation robot I've got like literally thousands of parts. They all look identical to me at this point, and the only way I differentiate them is by checking against the CAD and then measuring with calipers. And also, and these are drawn to scale. I haven't given these to you because they're really expensive. I use these ultra low head screws constantly when I don't have space. So clearly you can see that these ones go down to, this is 0.8 millimeters thickness, and this, at least for some of the M4s, is all the way up to 5 millimeters. So there's a, you know, your 4.2 millimeter difference is a huge difference potentially. Okay. One last thing that I noticed was a lot of you forgot, and again, this is fine, this is how we learn. In fact, I prefer that you make mistakes, because otherwise I don't know if you got lucky without knowing that you got lucky. So I prefer to see little mistakes that aren't catastrophic, because then we can talk about them and learn from them. The pulley flange for the belts. So this was our little 30-tooth pulley, right? And then this was the big wall. This distance here I set to be about 1.7 millimeters, and I set that so that the belt would be centered here. And what most people did was, this was just sort of willy-nilly whatever it was installed to, and then the belt was rubbing on one of the flanges. So again, the only way that you would have noticed this is if you had opened your CAD up as assembling and started measuring these things while assembling. But then I said to a lot of people, okay, so make that 1.7, and they're like, well, but there are no shims there, so how do I do that? And it occurred to me, an important thing to note is shims are not only, like, you don't have something precisely located only if you have a dowel pin or a shim installed permanently as part of the robot. Half of the stuff I do is installing stuff very precisely with jigs or dowels or shims, and then immediately removing those jigs, dowels, or shims. Because if I don't need it for it to stay there in place, then it just adds weight, right? So I'm going to show you a quick example. Actually, no, I'm not. Yeah, this is the example. So we don't need dowel pins or shims to keep this at this distance once it's bolted down, right? We only need 3 shims in here to get, well, I'll change that for a second. I think I got lazy and said you could do 1.5. It was better than 0 or 10. If we use 3 shims here, we put the shims here, smush this against, tighten the set screw, and we're done. And this is something I want to be very clear on. Most of the time that you're using shims and dowels, it's not permanent. It's just to get to the proper installation height or distance or separation, and then you remove them to save weight. Okay, so
How do you remove the shims?
I actually wouldn't use a shim. I would use a pin gauge, and I'm going to talk about that today. So this, as it occurred to me, some of these things, I thought, you know what? There's a whole lecture on just how to measure things and install things using measurement. I would love to give that lecture right now because it's burning on my mind, but for the sake of continuity with the last lecture, I'm going to finish up DC motors real quick, and I'm going to try to be quick, and then we'll go straight into measuring, and we'll finish that Wednesday. Lab 3 hopefully will go out Wednesday night, hopefully. Okay. So we introduced last time the concept of the DC motor. What are the 2 halves of the DC motor? Give you a hint, one rotates and the other doesn't. Stator and rotor. We're using running coil through the wire to make an electromagnet, and then that pushes off of the permanent magnet in the stator, and we may have a force. And then if I'm searching for things during the lecture, it's because the good doctors were here until the bitter end and didn't let me sit up. Come on. Okay. So I wrote down the electrical dynamics last time, so we're going to skip that. And then let's say this is for 12 volts. And I'll just give you the equation. Now you will note this is not on the tip of my brain. I don't know anyone except for Ed Carrier, who is a god of all things mechatronic, who has this on the tip of their brain. So I'm happy to write this down. I don't expect you to memorize it, just know where to look it up. So for some voltage, this is the voltage that we're driving the motor at, and let's say that's 12 volts for right now. R is resistance, K and KT are motor constants that we talked about, and we'll talk about some more in a second. Basically, we have a linear relationship between this could also be called theta dot of the motor, so the angular velocity, and this is torque. So if you're driving your motor at, say, 12 volts, then you have a linear relationship here. And this is omega no load, which means that there's the only load on the motor is just the friction from the brushes and the bearings. And this is, you've grabbed hold of the motor and it's not spinning at all. You can see omega here is 0. So this is tau stall. And someone tell me, even if you're not grabbing the motor, when do you see tau stall? Right when you turn on the motor. Okay, good. So if I am not pressing the motor shaft and it's rotating, I'm at omega no load and 0 torque. And then as I start pressing harder and harder and harder, I slow down and finally I stop. And then we talked about PWM. Remember, if that 12 volts, I would like to be able to control from 0 to 12. And the way I do that is called PWM, or pulse width modulation. And so what this is okay, so this is 0 volts, this is 12 volts. This is just our Boolean off on. And then this is our carrier frequency. Okay, so say, let's make this a typical frequency might be 10 kilohertz or 20 kilohertz. And then remember, if we the duty cycle DC is the percent of that period that we're on. We're at the high voltage. And so you can see if I expanded this all the way so that this took up 100%, then I would never be off, right? So on average, that would look like 12 volts. And then if this was 0%, then I'd see these just little spikes, or I might not even see them. And then it would look like on average I had 0 volts, so the motor just wouldn't be spinning. So then as I expand this, 20, 30, 40, 50, on and on, all we're trying to do is get this average voltage, okay? So if we did this really slowly, then it would just look like our motor was kind of going ka-clunk, ka-clunk, ka-clunk. As we speed up this frequency, it averages out, and it looks like here, oh, I'm running at 10% of 12 volts, but it looks like it's constant, like we're not switching. But we have to be switching very, very quickly. Now again, this is a deep subject, and the 218ers have seen a lot more of this than we're going to even brush on today. I'm not trying to teach you all of it. I'm trying to teach you only the bare minimum practical stuff that really matters in my experience. Is everyone clear on this average voltage thing? Okay. So typically you set this, if you're using a DAC card, you just say what percentage it is. With microcontrollers, you set output compares to give you percentages, etc., etc. They also usually have some type of special PWM generator to make it easy. But practically, there's a pain here. Oh, and just real quick, if we were to draw a graph, so remember, actually let me draw the transients, or the electrical diagram over here. So this is the supply, and then we have the resistor, R, and then L. And then this is the back EMF, which is kV omega. And then, okay. Now remember, VL is L d I dt. Okay. And this voltage here is IR, Ohm's law. And remember when I told you we got that equation over there, the linear relationship between speed and torque, by just ignoring L and saying we were at steady state, so the transients go away. But the transients actually do matter for what I'm about to talk about. And they matter quite a bit. Okay. So, this is omega, and then this is PWM, duty cycle. This is 0, this is 100%, and what we would like is this, right? Now let's think about this for a second. Steady state, no transients, constant voltage. So if I make this a different voltage, it offsets my line, right? My line starts moving this way. So maybe this is 12 volts, and this is 13 volts, and this is 14 volts. It's a family of curves, see? Voltage is setting our y-intercept. So what this means is, say just ignore torque for a second. Say we just have omega no load. As we start increasing the voltage, then we go faster. Okay? If we had an analog voltage like a power supply, this would be a no-brainer. You just turn the knob and you see it go faster. So this is what we should see, right? As the duty cycle goes, you can think of this as voltage. Say this is 12 volts. At 0% duty cycle, we're 0 volts and we have 0 speed. We're not moving. Now at 100% duty cycle, we're at 12 volts and we're going really fast, right? In actuality, this is not what happens. And again, I'm going to go ahead and pre-thank Ed Carrier. These are my notes from 218, and I'm using them because no one can explain this better than Ed himself. This is what's actually happening. This is duty cycle, and that's RPM. And it's cut off. This one here is 250 hertz. And you see how it doesn't go through 0? It should go right here, but instead it falls off. Then we get a little better at 1 kilohertz. And then at 10 kilohertz, we don't have this bump. It's perfectly linear, but we still have sort of a dead band here. That dead band is typically from friction. So, just so you know, if we were to do real low frequency, it'd be kind of like that. And that's bad. The best we can do is crank up the frequency like that. We're not going through 0, but it is perfectly linear. We just still have a little bit of a dead band. So we get another thing. So that's for increasing the frequency. So instead of doing 250 hertz, then we do 10 kilohertz, then we do 20 kilohertz. 20 kilohertz is sort of a magic number. Anyone know why? Can't hear it. So if you've dealt with motor drivers that use PWM and they're below this, you hear it's really annoying, as I just demonstrated. 20 kilohertz is about the range for typical young adult hearing. So would you want to go at 20 kilohertz? A little higher. You want to go, I mean, there's no reason not to. You're getting better linearity. And there's another benefit I'm not going to go into here, but basically bumping up this duty cycle to within reason. I think, Rob, what did the Copleys use?
Not sure.
Huh?
I don't know.
I think it's above 40 kilohertz for the Copley amps. Basically, you get better linearity between the PWM and the actual speed of the motor. So it's a better speed source, and you don't hear it. It's less annoying.
Is there a disadvantage?
There will be, at some point you're going to go fast enough it's just hard on your drive electronics. But I've never come to that problem. Okay. Yeah.
If you increase the frequency, does that mean that the inductance starts to matter more?
I think so, yes. Actually, I don't think it necessarily is. I don't remember. If you find out, let us know. I mean, the thing is, the reason why I'm being a bit glib about that is typically you're going to be somewhere around, I think, 20 to 48 kilohertz in terms of what you're doing practically, because hopefully you're not programming your own PWM signals anyway. Hopefully you've bought an amplifier, and the amplifier is going to be a black box where it simply runs at some PWM frequency, and that's what you're going to use because that's what it's hard-coded to be. And if it's an industrial grade amp, and it's good in all the other specs, then it's going to be fine for that. If you are doing it yourself, you're going to be limited by basically the speed of the microprocessor's oscillator, and so you're going to be trying to go as fast as you can. You're going to be trying to beat 20 kilohertz, but you may not be able to, and if you do, it will be barely. So you're not going to be like, oh, I'm going to go up to 48, because your oscillator won't necessarily be able to do it anyway, depending on which micro you're using. So practically, you either buy it and you don't care about it, or you're just damned glad you got as fast as you could from the microprocessor. But you did mention something important, which is I told you before, for this equation, don't worry about the inductance, just it's steady state, so di dt is 0. But let's draw the PWM. Okay, so let's say we just have 50-50, and that's voltage. So as we apply, if the motor's off, there's no current in it, right? If we're at 0% duty cycle, there's no current. And then when it's all the way on, then we have as much current as we can have, right? Okay. But because of that, the transient from the inductance, we have basically a rise time. So it looks kind of like this. Okay. So what I'm drawing here is the current, and again, that's because of the inductance. So if we were to get there, okay, so the time in which it takes the current to go from basically 0 to 63.2% of the full current that it can do is tau, the time constant, and that is L over R, where L is the inductance and R is the resistance. Does anyone know what this sort of chop waveform is called? Well, okay, well the shape is sawtooth, but practically what is that called? It's a bad thing, and what's it called? It's called ripple current. So for some voltage at steady state, we're going to get some current. This is an average current we'd like to command. Okay? Now everyone knows that the power loss, the heating power loss from a resistor is I square R, right? And from our electrical model over there, we have a giant resistor in the coils. So any current that isn't what we wanted is getting dissipated by heat, heating up our motor, and then eventually our motor's gonna, quit working. So if this is the average current we want, all of this current above it is bad. It's not helping to actually move our motor forward. It's just getting lost in the coils as resistive heating, and this is called ripple current because it looks like the ripples in the ocean. Okay. So what do you think we could do to minimize this ripple current based on that time constant? Huh?
Condenser or high pass filters?
You have a motor. What can you do to that motor with electronics? Analog electronics. I got some 218ers out here. That's not in my subset of options. Then I have even more resistive losses.
Change the speed?
I'm not doing that.
Diode?
Okay, we have two variables here, and someone just said R, and I shot that down.
Inductance.
We could change the inductance. So let's increase L. So if we increase L, the time constant, for this same PWM frequency, we're only going to get part of the way developed. Okay? Now let me draw that in a different color.
Can the time constant be bigger than the period of the wave?
Bigger than the period, yeah.
Okay.
If I understood your question, yes.
How easy is it to go into a motor and change the inductance?
Beautifully simple. Okay, so now we have the same. This is for clearly, if we extended this up, we could get over time. This is a terrible, terrible drawing, but over time, you can see if we kept going, we'd get to the same peak current. But because we're chopping right here at that period for the given PWM frequency, basically we can't get quite as developed. Let me draw over here just to make sure everybody gets it. Okay. So which one has a longer time constant? This is time and this is current. This one has a longer time constant, right? And this one has higher. But my motor PWM frequency is the same. I'm just going to chop it here. Okay? And then I switch the direction. So here I have higher ripple current, and here I have lower ripple current. Everyone see that? You don't do anything to the motor. That's the key, and that's the beauty of it. If we could, there are two things we could do here. We want to increase tau. We can either increase L or decrease R. You have the motor resistance you have in the motor. I guess you could put some resistors in parallel with it, but that's kind of screwy. Typically what you do is you just add an external inductor. What's an inductor?
Coil.
It's just a coil of wire. We just take some copper and we coil it up, and we're done. You can buy them for like $1.50 each off of DigiKey or Jamco or whatever. Now typically this doesn't really matter that much. If you're doing voltage drives, I haven't needed to and I haven't seen other people do it. If you know otherwise, congratulations. I do this a lot for current drives for haptics. So remember, haptics, we're doing torque equals KTI, and we were going to buy a Copley amp that we give it a voltage and it converts it directly to a current. Now there are two important things here. It's not magically just producing current out of thin air. It has a closed loop controller in it. So the way this works, you give I ref to the amp, and then it gives it to your motor, and we feed back around it, and this is I actual. Okay? So basically in our software we say, hey, I want 1 amp. And then in my software I will have said that means I'm going to give an analog voltage of 10 volts. That means 1 amp. So I give 10 volts. The amplifier knows how to interpret that and convert to a current command. So essentially we're saying 1 amp right here. Okay? Then it puts 1 amp, what it thinks is 1 amp, through the motor. Then it measures what the current actually was. It feeds back. It closes the loop. So basically we're just tracking whatever that commanded current is. Okay, now remember I said we're doing this because we want to do direct force control for haptics. Okay, this is chicken egg. Get prepared for the chicken and the egg to get confused in terms of their birth order. We're going to use Maxon Motors for haptics because they're damned nice, and we'll get back to that later. They're low friction, zero cogging. Everyone who does haptics, unless they're doing some type of admittance control, uses Copley amps and Maxon Motors. So let me write it up here. Maxon Motors, Copley amps. Just on average, and what I've seen both in our lab and other labs at Stanford, industry, and papers. Copley amps. Okay. This closed loop controller will go unstable and explode if you don't give it a time constant within the sort of bands that it can accept. So what happens with Maxon Motors is they're kind of special. If you took a Maxon motor and compared it to a non-Maxon motor of this, roughly the same torque or size, the inductance on a Maxon motor is insanely low for roughly the same resistance. What does that mean for the time constant? If the inductance is really low. So the time constant is low, and then what does that mean in terms of this ripple current if the time constant is really low?
You get to the peak.
You get to the peak. You have much more resistive losses, heat losses. So two things happen when you hook up a Maxon motor to a Copley amp. First, it heats up quickly because this ripple current, this excess ripple current, is just burning up in the coils. The second thing that happens is if you don't get lucky, your closed loop current control inside the Copley explodes, and the motor just starts spinning infinitely because it just goes unstable. So what do? We add inductance to the motor in series. So if this is our motor here, and that's the shaft, and these are the leads, you literally solder in a coil of wire here and a coil of wire here. And on average, between RE30s, 40s, 50s, and 10s, etc., they recommended, and I have seen it work pretty well, about 300 microhenries each. If you're going to scribble anything in terms of lectures this quarter, I might scribble today's lectures, because this is stuff that will save you hours of, oh shit, why isn't my motor working?
Why not just increase the velocity of this independence?
Huh?
Why not just take your maintenance down? That also something instead of adding.
The subject is deep. I'm not going to go into all of the reasons of the many different. Rob would like to. Rob, you've got 30 seconds.
If you're using a couple, you don't have access to generally.
Reason A. People are always convinced.
You can't fool around. If you could fool around with those parameters, maybe what you design your own motor app. If you didn't want to spend the time doing that, on commercial motor app, you got to play within the spec. So the Maxon will have that you can add in more reactivated code. It reduces the performance of the motor. It's speed.
Let me ask you a question about reducing the performance. If you don't add the inductance, but you need a Maxon motor and a Copley amp, and it goes unstable and sets your motor on fire, is that performance good or bad? I would say it's unacceptable. You are correct. We are slowing down our motor electrical dynamics, right? So if we want to do super freaking fast servo loops for haptics, we would want the fastest electrical dynamics possible. But if we're not stable such that the Copley torches our motor, that's sort of a non-option, right? So basically, you're only slowing down the electrical dynamics enough that you can be stable here in our closed loop control, and then after that, you have what you have. Please, don't build your own motor amps, especially if you're doing force control. Everyone who sees the equation says, hey, I could screw with R. Sure, you could screw with R, but there's no reason to. Building robots is really hard, and there's no reason to start screwing with variables just because it appears in the math, just because you can. What I'm teaching you is the simplest, easiest way to get running and do things. So, let's review. Haptic device equals tau equals KTI, direct force control. Maxon motor, zero cogging, low friction with precious brushes. Copley amps, they're easy, they're tested. We have some from the 1970s that are still working. Add an inductor, slows down the electrical dynamics so that A, it's stable and we can use it, and B, it doesn't torch your motor. Let me give you a quick example. I had some, so let's talk about Maxon Motors. Who here knows the term RE in reference to Maxon Motors? So only two people. Okay, so Maxon Motors, they have different series. They have A series, A Max series, RE series. Most people who do research in haptics use the RE series. Okay? So then the next thing you do is you say, I want a I like the 30 millimeter motor. It smells good. So I'm going to do an RE30. RE-30. That means it's RE series, and it's a 30 millimeter diameter motor in terms of the overall core of the motor, or the outside. And you guessed what the part number would be for a 40 millimeter RE series? 40. How about a 50? And how about a 10? It's a 10. Maxon is one of those nice places where the part number means something about the object. Okay. RE10. So I had been showing RE30s and 40s, no problem with my 300 microhenries. And then I got an RE10 and I torched it immediately with the same inductance. Anyone know why? Physically, why? Huh? There's a different type of coil. So for the tinier motors, you use tinier wire. And the tinier wire, the higher the resistance. Remember? Okay. So my resistance went up, so my tau went down, but I had the same 300 microhenry inductors, so tau went down, which meant I had more ripple current, which means I torched the motor, even though it's a Maxon and it's a Copley. So what you want to do is you want to be real careful when you plug in a Maxon motor to a Copley amp that you have your finger and thumb on it as you're starting it up to make sure you're not torching it. And if you really want to understand this stuff well, there's a guy named Dean Crumlish at Copley, who's like an expert at this. They will not connect you to him. Don't try. Somehow get his number, call him directly. He's super nice. And he will tell you all of this, and has. But remember, RE10, the smaller equals smaller wire, higher resistance, lower tau, higher ripple current, torch. Uh-oh, I'm not plugged in. Who brought in my laptop today? Anyone? Do you know where my plug is?
It's in the hallway.
Shit. Okay, so we're going to take a brief intermission as my computer crashes. Give me one sec. Oh man. Does anyone have a power adapter for a Dell laptop? May I borrow it, please? Ah, here it is. Never mind. Sorry. Your generosity is appreciated. Yeah.
You want to say why PWM instead of a linear amp?
I actually don't know. Feel free to explain though.
Okay, so the reason you use PWM is because the power is always either all the way on or all the way off. So it's much more efficient. If you have a linear amp, like old style, you're trying to get half the voltage out, you're dissipating half your power in a big heat sink. So that's why amplifiers and power supplies have been anything so small, but they're all pretty much PWM.
Way more efficient.
Okay. So I'm going to skip around a little bit. Again, there are many books and dissertations on and courses on motor control. Let me see if there's anything else. Ah, yes. Okay. Let's talk about thermal usage of motors. Actually, you know what? Let's look at a Maxon Motors spec sheet. That will be helpful. God, I hate this. Come on. Okay, so this is an RE30. I'll show you a few things real quick. Remember that front bolt pattern we talked about last time in terms of screwing it to a plate? That's this right here. So it specifies what type of screws, what the diameter, what the spacing. This is the back bolt pattern, and this tells you how to CAD your encoder adapter plate, because you're never ever in a billion years using adhesive, right? Okay, and this specifies the front shaft here. This specifies the back shaft here. And then you can see this 30 millimeters. This is a 30 millimeter diameter one. Anyone know where my mouse is right here, what that is? Huh? Can't see the mouse. Well, that would be problematic, huh? Can someone get the lights, please? Keith?
Is that for centering?
This right here. That's for centering the motor. All right, so if you plug it into a plate, there's a hole for locating it exactly as we did. We used the flange of the bearing for the roller blade pulley. And how about over here in the back? The exact same thing. Now again, remember, cheap motors often don't have back shafts, or they often have back shafts that are so tiny you can't fit an encoder on them. Some Maxon motors, and I don't know why, have really short shafts. Make sure that you're going from the spec sheet so that you see what this distance is, 15.7 millimeters, and in your CAD put the encoder and the adapter plate on first before you order the motor to make sure you can do it. And you're going to be using this little hub here, front and back, to line everything. Okay, let's look at a few numbers here.
I have a quick question.
Yeah.
What's the difference between the A-series motor and the RE-series motor?
No clue. Not sure. I think I looked at them a while ago, and the REs were a lot nicer. Part of it may be precious brushes. I can't, off the top of my head, I don't know, but you typically want the RE for nice stuff. Yep.
And when you design your encoder adapter plate, do you have to just steer clear of the leads on the
Yeah.
shaft?
Yeah. So let me find something for a sec. Okay, so this is an adapter plate. Now, the reason this is sticking up, this lead, is because I didn't feel like bending it in SolidWorks. But you just bend the lead out of the way. You can see with this adapter plate here, I have a lot more room to bend this lead without hitting the encoder. And so this motor here, I'll show you that this is downloaded from Maxon's website. Okay? Now, quick hint. You see how it has this is the back of the motor, and see how it has the leads and it has the screw pattern? Never use CAD to design things, ever. If it's not on the spec sheet, it's not correct. From Maxon, from Stock Drive, to Masumi, to McMaster, every one of them has screwed me with CAD that was incorrect. Typically, they put all their resources into actual black and white, orthographic and isometric drawings, and that's the Bible. So if you call them up, and I think it's actually in their laws somewhere in the user agreement, if you call them up and say, hey, my robot was built around your 3D model and your 3D model was incorrect, they say, too bad. If you say, and your drawing was incorrect, then they may, give you some money, or at least be very apologetic and send you a free part. So this model is useful, but if this one disagrees from the drawing, go with the drawing and contact them and get it fixed. Okay, so again, and you can see this little hub here? That's what I use to center the adapter plate on. And then this one here. Anyone know what this is? So this is the centering hub. This is the shaft. What's this? No? That is typically some type of retaining ring to take out some of the axial play in the motor. Don't use that. Again, this is an issue of if I were to put a motor on the microscope I could show you, it doesn't look anything like that. And, so if you were to download their CAD and think you could use that, that would be very bad. And then let's come back in here. Okay, so again, here you see my encoder, and then this is my adapter plate. See, these screws keep the adapter plate on the motor, and then these screws keep the encoder on the adapter plate. And these little notches in my adapter plate allow me to solder wires to my motor terminals without shorting anything. You want to be real careful with these motor terminals and this plate. Anyone know why? If it's a metal plate and you touch both of them to the plate, you have killed your motor. Now let's take a look at this motor. See this? Remember I showed you this? This is a helical shaft clamp. So what this does, let me come back here for a sec. Okay, so here's my motor. Here's the pulley I want to drive. Here's the plate all of this gets bolted to. I have one bearing, two bearing. So the shaft of this pulley is supported on the bearings, and then I'm connecting torsionally the motor shaft here to the shaft through this flexible coupler. Someone tell me why. Why don't I just put the pulley directly on the motor shaft? There are several reasons.
You don't want back to
I don't want the radial loading. Okay, so I'll write that down. Let's get some more reasons. Anybody? No, we can do that. Yeah, so let me draw it out for you. So here is the body of the motor, and here's the shaft. Now I could just put the pulley right here. But then every time I take out my motor, say I want to change the encoder and it's much more convenient to take the entire motor and encoder assembly off, I have to take off the pulley. And when I take off the pulley, I have to take off my belt. And when I take off my belt, I have to literally take the whole damn robot apart. Were I to do this on my robot, it would take, 24 hours to do probably. So what I'm going to do instead is I'm going to put another shaft here. Okay, I'm going to support it with bearings. Okay, and then I'm going to put my pulley right here. And then I'll put little flanges, pretty little flanges, okay? So let's talk about this for a sec. I could just, in theory, take a stick of steel and weld it here and here. Would that be a good idea? It'd sort of defeat the purpose of being able to take the motor and the encoder off. You know, say we have a belt coming off of this and I really don't want to disassemble it. So I'm not going to weld anything. It needs to be temporary. The like gold standard of doing this is to use a flexible shaft coupler. So it's essentially a giant spring. It is low stiffness in flexure and high stiffness in torsion. Taru, can you please open the blinds all the way? And then Samir, can you get your blinds, please? I'm losing half the class here. So look up at this. You can see these slits are able to bend back and forth like this, but torsionally it's very stiff. So it transmits the torque, but allows what? It allows misalignment. So say we take our motor, and actually it's like this. This is kind of cartooned. I could take the same motor and I can withstand axial offset and also angular misalignment. So if this is my axis, not only can I move it up, so I have axial misalignment that way, I can also cock it at an angle, and that misalignment gets taken up in the helical thing. Now, it won't break this within certain bounds because that's what this does. This is designed to do that. If you don't have this and you were to simply put the motor and weld it directly, it would kill your motor in about 5 minutes. So in terms of why we do this, why we use the flexible shaft coupler, I like to call it hot swapping. Say what might happen next month when I turn my robot on is I find out an RE30 isn't big enough. I need more torque. Well, because I've done it this way, literally all I do is undo 4 bolts, 1 screw for the clamp, take my motor off, I put on an RE40 or 50, 4 bolts, 1 clamp, and I'm done. I don't have to take apart crap. Yep.
What are some good part numbers for those flexible shafts, and where can you get them?
You can get these on McMaster, on Stock Drive, on Nasumi. I think maybe well, I guess it's right here actually. On Nasumi, this would be called CPLCN. And the one that you just saw is 20-5-6. Somebody tell me what these numbers mean.
Turns?
20 is the diameter of this, in terms of the big diameter. So let's draw it for a sec. So typically when you're speccing these things, you have a length L, an overall big diameter D, and then we'll call this a little d1. This is a little d2. What are d1 and d2? They are the diameter of the shafts that are coming in and out. So in my case, I have a 5mm motor shaft and then a 6mm shaft after the bearings. So that's what the dash 5-6 is. The 20 is the overall D. Now, depending on the manufacturer, the part name might also include L. Okay, they have set screw versions of these. They suck. Try not to use them. Mm-hmm.
If it's misaligned, then does it like align it, or
No, it doesn't align it. It flexes. So remember, this is high flexural compliance, and then low what? Torsional compliance.
isn't that like ultimately bad? Will you lose some energy that way?
Of course you will lose energy, but it's going to happen either way. Because when you machine things, there are tolerances, and they are going to be misaligned some percentage of the time. So the question for you is, given that you're going to have misalignment, would you like to be able to not break everything or still break everything? Because it's going to happen either way. Yep?
Or is life space, or is it between the
This?
no, the pillar screw.
That?
The vertical pillar.
This?
Yeah.
Those are the offset plates, or the offset shafts. So basically you can see, if we go back to my motor assembly, which may take a sec. Come on. So this as a unit simply plugs into the plate. So this is the 4 screws I was talking about. 1, 2, 3, 4. And that supports the motor. And then I put the other shaft in right here. I do the clamp and I'm done.
And those offset screws don't cancel out the
Nope.
Okay.
These are screws. These right here, oh, SolidWorks is great. This right here is a bolt hole. Should I be locating anything with bolts? No. So these don't do jack in terms of aligning it. Okay, let's take a 2-minute break to stretch our hands because we got some sleepy people. Let's do some jumping jacks. I'm going to turn on the lights. Hey Rob, can you give me a mic check, please? Can you see the mic? Good. So we're still recording? Okay, we're going to start again. Someone please turn off the lights. Camille, can you please get the lights? Okay. Some of these parts are scattered about. So is everyone clear on why we're using a flexible shaft coupler? Sort of. So I'm just going to real quick show you a few just so you see what they look like. Yeah.
There was a quick question in the break about whether or not you're trying to actively locate your motor, or if you're just going to use the flex coupling so it's not allowed.
No, I typically try.
And so the question was, how are you doing that with only those 4 standoffs?
That particular assembly I don't remember offhand, but they're all the tricks you've been learning in the lab. There are tricks for all of this. So if the question is there a trick for doing it, the answer is yes. But this is deep in my robot. Off the top of my head, I don't remember what the trick is. Okay, let's look at these real quick. So these are flexible shaft couplers. This one's even got a shaft in it, handy dandy. Watch this, ready? It's bendy, flexible, see that? And I don't have another hand, so I can't spin it. Hey, you want to spin this for me, please?
Is it in all directions?
Just
Side to side.
so you see the flexible compliant, and now just spin, try to align it as much as possible and just spin. And you're not going to see anything because nothing's happening. It's very stiff in torsion. Cool. So we have different sizes. This one's muy pequeño. Look at this. Real little. Now some of these are called bellows. Some of these are called helical shaft couplers. I don't particularly know what the difference is. I always just get ones that look like this because I've been using them for years and they work great. Now, some of you who've done 218 will have used ones that have interlocking fingers. I hate those. Don't use those for precision robotics. They suck. Please don't use them. There's no reason. Just use the helical shaft couplers.
Like spider.
Yeah, spider couplers. Those blow. Don't use those. Okay, let's talk about how to connect to the motor shaft. Someone give me the first idea that pops into your head. What we just looked at. Well, sorry, I was trying to be funny. This. Okay, there's another way. Which is, what's the other way? What's the other way we've done in the lab? Set screw. I'll give you the hint on the set screw. They vibrate loose constantly. So you tighten it down, then you run the motor for 5 minutes, and it backs out. It's probably going to back out and get lost in your machine. You'll then have to get a new set screw. You will have to service the robot, and if you're me, you'll continually get unlucky, and that set screw will get in between a gear of some type or a slide and will break everything. Set screws suck. Seriously, they're like the devil. I try never to use them unless I absolutely have to, and I've gone to some pretty extreme measures. I've even made my own clamps just so I don't have to use set screws. They are very bad in terms of servicing. The other thing is then you have to modify your shaft. However, for a given size, they have much higher torque carrying capacity than clamps. So you can have a clamp with super high torque capacity, but then it's going to be a wider diameter. So I could make a miniature version of this clamp with set screws only that has triple the torque capacity, and it's smaller. So it's sort of a trade-off, right? If you need small and huge torque capacity, you have to use a set screw. If you can get around it, try to get around it. Now, another hint, a lot of these little miniature robot things, the set screws are tiny. I've used M1.6 set screws. I've used M2 set screws. They all strip, they all suck. And it's one of these things where it's like, you think it's going to be okay in CAD, but then you spend literally a week of your time doing nothing but dealing with set screws, and you're like, wow, this sucks. So I considered giving you a lab that tortured you with set screw couplers, but I'm going to save you the effort. Just don't do it. It's as bad as having to sand shafts or use 0.5 millimeter stack shims. Yep.
Can you still use that for something as tiny as like an 1/8-inch shaft?
Oh yeah. In fact, this right here, I think this right here is for an 1/8-inch shaft. Okay, we could press fit. I don't like doing press fits if I don't have to because they're usually permanent. Yep. Thank you. That's right here. So the other way is called a key. Now, Keith, can you get the lights, please? This is your daily calisthenics is getting up and sitting down. Okay, everyone. Oh God. Okay, maybe undo some of those. Okay, this looks good. Everyone see that there's a little nodule on that, the black nodule on the shaft. So that gives us positive engagement with a pulley. And then here, you see the notch cut out of the shaft there? That's basically the negative of that, where you install your own key. So let's talk about how that works. It's called a key, like a key to a door. And it will either come on the shaft already, like this, and so then your pulley shape will be like this, or it will be the inverse, where it comes like this, and then you hammer in your own key. They can be pretty tricky to get that key in and out. They're for super high torque. So this motor is a scooter motor, so that's probably like a 150 watt scooter motor. These are gigantic gear heads. That's why we're using keys, because to build a clamp that could take that torque would be like the size of my hand. And set screws vibrate free. So this is, they hammer in a little wedge called a key. So if this were the pulley here, then you would have a separate part. This is called the key, and you would literally hammer that in. And then you, actually you'd have a little notch here, like that, okay? So you'd hammer in the key, and then you'd be coupled torsionally. I've never needed that much torque, and I hate keys, so I refuse to use them. So let's make a like an axis of evil list.
Why
Why do you hate keys? Assembly?
Because anything you have to hammer together makes me nervous. And then to hammer out. It's the axis of evil. Nuclear. This is, I'll put set screw at number 1, followed by keys, followed by press fits,
Spider couplers.
followed by spider couplers. Just don't do them. I've already done all the R&D for you in terms of years of annoying assemblies and maintenance. You don't need to reinvent the torture. These suck. Use clamps. Okay. Let me see what else we got. Cogging. Someone tell me what cogging is.
Can I ask you one question before?
Uh-huh.
How do you know how much torque can a clamp handle?
Say it one last time.
How do you know how much torque can a clamp handle?
The clamp manufacturer will list the torque capacity of said clamp. And if they don't buy it. If they don't list it, don't buy it. Because there are lots of clamps where you're like, yeah, that's pretty big, I can handle it, and it can't.
So is there like, I mean, if I have like a 50 watt motor, it's in watts, right? And then you have some torque, what the heck how do you do this?
So in your robot, you're going to know what you want to be doing, hopefully. So I don't know, a scooter, you'll know you got a fat guy like me going up a hill, and so the speed and the torque, okay, so now you've got the torque. And then you know what the gear ratio is, so you know the ultimate torque on that shaft.
Okay.
And then you look up in the motor, the coupler guy is going to say 2 Newton meters max. And so if you have 3 Newton meters required, then you can't use it.
Oh, so you do it the other way around. You don't go from the motor, you kind of over-dimension the motor and you set your thing based on
Yeah, you always over-dimension everything. It's called factor of safety. If you need X and you give X, your robot will fail half the time. You need like 2X or 3X or 4X. Let's talk about cogging. I'm going to hand these out. I need these back at the end of the day. These are cheap Chinese motors that go in, I think these go in drills. And I want you to spin them. And here, just take the box, spin them, and tell me something obvious about them. They have discrete positions. That's bad. This is a DC motor, right? Not a stepper? Is everyone sure that everyone sure you're holding a DC motor, not a stepper? It's a DC motor, so DC motors are for continuous rotation, not incremental. So why do you have little detents in it? Cogging. So remember, I told you that motors have rotors and stators. Okay? So this is our stator. It's staying in place. And I'm going to have a ring of magnets. These are my magnets. Okay? And I'm going to have a magnetic field lines in between here. And then my rotor in here. So this is stator. This is rotor. And the rotor's attached to what? The shaft. So this is spinning. Okay? And how are we spinning? What are we doing to make the spin motion? Magnetic field. So we have a coil in here, and we're pumping current through it. Electromagnetic fields hate going through air. They just don't like it. So what you do is you fill this space with a ferrous core. This is a ferrous core. Anyone ever heard of magnetic permeability? And I think they normally call it mu. So basically, the magnetic permeability of a material says how desperately that material wants to take the magnetic flux through the material. Okay? So air doesn't particularly want flux through it. It could care less. Iron is it's a gobbler. It really wants all of the flux to go through it. And what that does is it helps clean up the shape of the flux lines and give us better torque, better performance. Now, has anyone here as a mischievous child taken your parents' silverware and stroked it with a magnet for a while? I'm the only person who... So I used to take magnets and magnetize all of my mom and dad's silverware to screw with them. If you take just a chunk of iron or steel and repeatedly and prolongedly expose it to an external magnetic field, it will have a residual magnetic field often. And it's a property of ferromagnetic materials. Okay, so literally take a bar magnet and just stroke a fork for like an hour, and it'll be a little weak magnet. And then you can control it under the table and say it's a ghost. Grandpa's here. So the problem is this ferrous core is not a magnet, right? We're only having it here because when we turn on the current, we want to route the magnetic flux lines more cleanly to get higher performance. The problem is it's just like the fork in that if we do that enough times and for long enough, we have some residual magnetic field. So now we have a weak little magnet here. So then as we get in different positions, with the power off, the two magnets want to interact. So that's what you're feeling. You're feeling a cheap motor that has a ferrous core that has been magnetized a little bit, with just a little bit of a residual magnetic field. And that's what's causing the cogging. Okay? So, recap. Flux lines from the motor coils don't like to go through air. We're going to route it through a ferrous core to clean up and get higher performance. We induce a residual magnetic field in the ferrous core, and then we're interacting with the permanent stator magnets, and that gives us cogging, which is bad. So, yeah.
So, how does a better motor correct that? Because I feel like that should be a problem in everybody.
Maxon Motors have zero cogging. Do you know why? They're called coreless motors. They literally do not have a ferrous core. So this is one of those other deep rabbit holes. And if you really want to know, you can call them up, or you can ask Morgan quickly because he's an expert at this. Maxon has patented ways both for making and designing the coils such that they don't need the ferrous core. So they have higher torque even without the ferrous core. And then because they don't have a ferrous core, they don't have any cogging. Did everyone catch that? Maxon Motors, no ferrous core, no cogging. Nice.
How much have you paid?
Huh? None. Same thing as Masumi. I just, I got tired of having shitty robots, so I started using the nice stuff. Okay, so this is this is from Servo City, a fine purveyor of shitty motors. And this is another Chinese motor with a ferrous core and serious cogging issues. Now, unfortunately, none of you can really see it, but I can take my wrench, and can you zoom in, Rob? If they're cogging, do you think you'd see this continuous motion, or would you see ba-bump, 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 ba-bump? Yeah. So where'd my cogging go?
So heavy of it?
Nope. Where's my cogging? I guarantee you it's here. Why can't you see it? Gearbox. You can't get rid of cogging, but you can mitigate it through usage of a gearbox. Say you don't want serious torque, so you don't need a gearbox. Okay, well, too bad. Because what you can do is you can use a gearbox not just for torque increase or speed decrease, you can use it to get rid of nasties in the motor. So, basically, does anyone know what else this fixes? Let's talk about this in a more general case. Can everyone see if I'm over here? Let's say we're not going to say it's a gearbox. We're just going to say a gear reduction. And for the sake of argument, I'm going to say it's a cable gear reduction so that I don't have any arguments. Okay, so this is a motor or a gear head. It could be either one. Let's say it's a gear head for now. Well, I'll leave it up. Okay, and let's say that this is a 10 to 1 reduction. That means I turn this 10 times for one time here. Okay. Now let's say that my cogging happens every 10 degrees on the motor. Cogging is not independent of gear heads, it's just in the motor. So how many degrees am I going to experience cogging on this cable shaft?
100?
I heard conflicting reports.
So you have a 10 to 1, so the gear hits.
So this has to spin 10 times, the motor shaft spins 10 times to get one turn here. Okay, and I have little cogs.
Yeah, 1 degree.
Yeah, so now I experience the cogging at 1 degree. Okay, now let's say this isn't a motor, this is a gear head, and I have backlash of I don't know, 2 degrees. So what's my backlash here? So what's my backlash here? 0.2 degrees. So the reason I tell you this is because gear reductions, such as a cable transmission, aren't only to increase torque or decrease speed. They're also to get rid of bad performance out of a motor or a gearbox that you otherwise can't get rid of. You can't get rid of backlash. You can't get rid of cogging. Well, I mean, you could choose a different motor or a different gearbox, but you're still going to have some badness at some point. What's important to know, A, you can't get rid of it, but B, how you mitigate it. So I can reduce my cogging and my backlash by throwing like a cable transmission on. Yep.
So you're saying that every 1 degree it's cogging?
Yes.
So how is that better than every 10 degrees?
Because if I make this 100 to 1, now it's 0.1. And at some point you're going to cease to feel the cogs, right? So this is a backdrivable motor, very easily backdrivable. And it's shitty, so I guarantee you the cogs are pretty wide apart. And yet you can't see any cogs. So I could use this just fine on my robots without any problems. So at some point you still have a nice backdrivable compact motor where the cogging isn't bothering me at all. That's why.
It just becomes part of resistance. Is that what it is? You just uniformly distribute the cogging so that you just have a little extra resistance.
Exactly. You have some spatial resolution, and if you go below that, you know, for feeling cogs, and if you go below that, it doesn't matter, right? Say your spatial resolution is 2 degrees for a cog. If they were at 2 degrees, you could still feel it. All right, so go down to 1, and then you can't feel it. It's still there, but you've mitigated it. So let me ask you a question. If you wanted to go from a motor to your end effector, and you wanted 100 to 1 reduction, which is better? To do a 100 to 1 gearbox, or to do a 10 to 1 gearbox followed by a 10 to 1 cable capstan? Now think about this for a sec. Gearboxes have backlash no matter what. So the 10 to 1 is going to have backlash, and the 100 to 1 is going to have backlash. In the end, I'm going to have the exact same speed torque profile at the output. If I split the gearbox into a nice compact 10 to 1 and then a nice compact 10 to 1 cable, I've gotten rid of, I've divided my backlash by 10, and I got it basically for free. So oftentimes when I throw a gearbox on something, I'll split it. I'll use a motor with a gearbox, but if I needed 100 to 1, I won't buy 100 to 1. I'll buy 10 to 1, and then I'll have like a cable transmission or something to then take the backlash off of this and divide by 10. It's a smart way of dividing.
But isn't that like a trade-off, because you kind of said don't use cables unless you really need to?
Yeah, and if you have nasty backlash in a robot arm, you often need to. So the problem is backlash in a serial manipulator like this will kill you because it's the RD theta, and the R is high. So even for small d theta, you get huge. You know, this is when you watch robot arm movies and they're doing this. Often that's backlash. I'm going to hand out these. I want them back, even though they're wasted. Can you put those behind you? Let's talk about something else. Oh, we're not going to get to measurement today. My jello is going to melt. Okay. Let's look at some electrical specifications for a sec. Someone please turn off the lights. You know, if I were good at technology, And if I were at an institution that were good at technology, I could probably figure out how to put a light switch right there. It's beyond my engineering capabilities, though. Okay, so let's just take a sample motor. Let's do 24 volt. We'll do 48 because it's easy to locate. So this is the nominal voltage here, 24 volt. This is the voltage our PWM is going to be banging between 0 and 24, or 48 or 18. You want to match these motors as much as possible. So if you buy a 48 volt Maxon, don't have a PWM voltage of 24 volts. You want to use the voltage, the nominal voltage they've recommended, because then all of the math works out. If you mismatch them, the data sheet is basically not going to work for you. This is the no load speed. This is how many RPM it's going to spin at without any torque. The current that it draws at that, 78.5 milliamps. Let's do, all right, now look at this. Max continuous torque, max continuous current. Anybody know what that is? And then look below it, you see stall torque and starting current. So let's see. Here the max continuous torque is 88.2 millinewton meters, and then the stall torque is 1.02 newton meters. So the stall torque is over 10 times as much as the continuous torque. So let me tell you what I mean by this. Stall torque means it's, starting from rest, and you get that spike of roughly 1 newton meter, or you grab it and stop it. You can't do that for long. It will burn your motor. It will literally catch fire if you do it for too long. Max continuous current and torque are different sides of the same coin, because tau equals KTI. So what you're interested in is, what is the torque that I could literally leave on for a week while I go to Hawaii and it will not burn down the lab? Don't run it past that unless you know damned well what you're doing. So basically, the resistive loss I square R in the coils? That's the power we lose from the current. This is square, right? So as current goes up a little bit, the power loss is going up quadratically. So, and what that heat is doing is it is breaking down the insulation between the individual coils of wire in the rotor. And then eventually it's going to melt something in there, which is going to get in the bearing, so it will cease to spin, or it will just short across the loops of wire and then fry your motor. So has everyone felt how shitty those motors are? Those were driven at stall torque for too long. If you drive at stall torque for too long, your motors will likely feel like that. Well, this is kind of crappy, right? Because the no load current being through 78.5 millinewton meters, and stall torque being 1.02 millinewton meters, and then roughly a factor of 10 or 11. Too bad. The only time where you often really have to do stall torque to get their performance as haptic devices, in terms of what I've done, because of the do I want to go into that? I don't want to go into that. There are lots of reasons. Let me suffice it to say, you can drive at stall torque, which is called peak current. Peak because you can't exceed that, for very small fractions of time. We're talking like 1%, 5%. Maxon will give you an Excel sheet with thermal specifications where you type in what percentage of stall torque you're doing for how long at what duty cycle, and then it will tell you, okay, if you do that, how long you have to let the motor cool off before you're allowed to use it again. And so for a lot of these things, if you use stall torque for like a second, you're going to be cooling off for 10 seconds or 20 seconds. So this is bad, right? Because then your robot is it's going to be like awesome performance, and then you can't use it for like a minute. So what this is good for, the peak current, is basically when you the cleanest way to get more torque is to have a bigger motor. And for haptic devices, you would like to show, hey, we're able to render huge forces. If in your calculations for paper you use the max continuous current, your haptic device looks terrible. And then if you use your peak current, then it looks great because it's a factor of 10. So what people do is they always report the peak current in their papers on haptic devices because it looks great. But if you were to then plug in their haptic device, it would set on fire. So like if you go to Sensible's website, they sell the Phantom Omni. All their specifications in terms of dynamic range and max force, I believe those are all for peak current. Now thankfully they have a little check on that doesn't let you drive for too long. They have a thermal model of the motor that keeps track of how hot it's getting and then shuts off before you torch it. Most researchers don't have a thermal model. So the reason I say this, we had a PhD, Kurt Salisbury, do a haptic device in our lab, and in his papers he did peak current. Okay, and that's completely legit because literally everyone who does this does that to make their haptic device look better. But just keep in mind, you can't actually buy that haptic device and use it at those peak currents because it will torch. So what you need to do for your robots is you really, to be safe, you want to spec it for max continuous current. And if you need more juice, you need a higher gear reduction or a bigger motor. Yeah?
Doesn't the motor cool down faster if you let it spin fast and it has that little fin in the back? So rather than stopping the motor and then restarting it,
You're talking about drill motors that have little fans, and Maxon Motors don't have little fans. So yes, you're right.
looking at this one has like little fans too. So
That's a really cheap Chinese-made motor, literally taken from a drill.
okay, so normally motors don't have.
Normally motors don't have little fans in them.
So I see that like they spin and then you have a gearbox that actually connects and disconnects. So your motor is always spinning, but then you either connect or disconnect.
Not the case for precision robotics that we're doing.
Okay.
Now, what would happen if you were Lewis Whitcomb and you were doing underwater robotics? Would these max continuous currents be the same? If you had a motor undersea with a giant heat sink of water? No. So keep in mind, there are some special cases, such as underwater robotics, where you can actually drive much nearer to stall torque because you have, compared to the size of your motor, the infinite heat sink of the ocean to cool you off. And you can play tricks with fast convective cooling, but most people in research aren't going to do that. So
it's the same motor?
same motor, yeah. So Maxon is assuming that your motor is in air, okay, as most motors are, and that's a pretty safe assumption. But just know there are some special circumstances where if you're doing underwater robotics, all of this would change. What you need to know as a takeaway from today is stall torque can only be used for the duration of turning on your motor. And if you want to start using it regularly, like saying you're doing haptic devices where let me tell you what happens if you rely on peak current for a haptic device. Before it torches, say you do make a thermal model, okay, so it doesn't torch. So my haptic device, my proxy is about to hit this wall, and I want it to feel crisp. So high force, great. If I'm tapping, this is perfect. This is low duty cycle. My motor gives me a little extra punch and has time to cool down, okay? Now as the frequency increases, I have less and less time to cool down. At some point, if I have continuous contact and I want to keep that same force, what's going to happen? My computer's going to say, we're getting too hot, I'm going to decrease the torque, and it's going to feel like it'll feel like this. You hit the wall, and then it goes. So with the Phantom, the Sensible Phantom Omni, you can use peak currents, and then if you start getting aggressive with it, it just goes. And that's really not realistic. Anybody? Nope. Okay. Okay, let's look here. See this? Axial play, radial play. That means wiggle. That tells you how much wiggle you get. This is all the thermal stuff for making a thermal model. If you're really interested in that, contact Scott Hamilton at West Coast Maxon Motors, and he'll give you the spreadsheets. Here's what's very interesting. Max axial load. Max force for press fits. Max radial loading 5 millimeters from the flange. These are the Bible of not breaking your motors. They are serious. They don't mean if you get there it'll sort of work. They mean it will break permanently. Don't get near it. So let's draw a motor. Okay, here's the shaft. What direction is this, and what direction is this? Let's start with this one. Radial, axial. Okay, so axial, unless you're doing something odd, say you had a helical gear, like a big honking helical gear that gives you an axial thrust load, you could have that. Mainly this is for press fits, which is when you're hammering on a press fit, A, don't do that, and B, it will break your motor because it'll exceed your axial limit. For an RA30, it's 5.6 newtons. That's pretty low. You're going to do a lot more than 5.6 newtons putting a press fit on. So if you try to press fit directly on the motor, it'll break. Any clue how we could get past that? No?
It says shaft supported.
Why are we holding this mid-air while we press fit? If we put this on the ground and support the back shaft, then we can apply more load so we don't kill our bearings. The axial and radial loads are all about bearing loads. So if we actually support this so it's just one solid steel beam, we can have much higher press fit loads in axial. Do you always have a back shaft? No. Do you always have access to your back shaft? Maybe you put on your encoder first. Maybe you press fit on an encoder wheel, because we're really dumb today. So you can't be guaranteed that you're going to be able to access the back shaft. Okay, now what happens when we want, that's just for installing. What happens when you take your press fit off? Now we can't use this trick. Now we have to grab onto that, and grabbing onto the back shaft is even harder than grounding it. So just don't press fit. It's bad. It will kill in the axial direction the bearings. Let's talk about the radial load. Lab 2, belts. Belts are terrible for radial loading. So we tie a belt around here and we yank, and we have twice the tension on the belt, right? Tension, tension, 2 tension here. Now notice it specified max radial loading 5 millimeters from the flange. That means it's not that you can take the same force and apply it 20 millimeters. It means 5 millimeters. It's specifying a torque, right? We have a force and we have a radius. And this is this is what influences how you put on a pulley. So let me come over here and draw this. Many pulleys look kind of like this. So we have a flange, then we have the teeth, we have another flange, and then what's this called? What's this part here? The hub. Okay? If we're doing a clamp or set screw, we have this hub. Okay? We have this motor here. Now we're not going to change anything about the motor. This is a thought experiment. I'm free to put this on this way or to flip it upside down. And put it on this way. Which is better and why? The left. Why? Because if this is the center line of my force, this is a lower lever arm. I'm going to take this opportunity to remind you all that there is nothing but details in mechanical design. There is no big picture. There is no it'll work itself out. Even if you're trying to decide if you want to put your pulley on upside down or right side up, there's always a damned good reason for why you pick one over the other. And the sooner you embrace the monotony of those details and their importance, the sooner your robots will work flawlessly. I spent a long time putting my pulleys on the wrong side, and then someone showed me. I'm like, oh man, I've been killing my motors all these years for no good reason. What's another good reason, by the way, for this? These are set screws as I've drawn them, which means I have to put a flat on my shaft, right? Okay. And this one, the flat has to come all the way down here. On this one, the flat only has to come right down here. So you have to Dremel less. Okay? Now, remember, I showed some of you over the weekend, when you're Dremeling on something nice, you're going to put a plastic tarp and duct tape everything, and you're going to have a vacuum up here while dremeling. Okay, let's back up for a sec. You can buy motors with flats on the shafts. Sometimes the motor you want doesn't have a flat on the shaft, so you dremel one on. There's no way around that. Maxon hates making custom motors. So you're going to dremel this. Do you want to dremel to here or to here? You want to dremel to here. Okay? Now, one other thing about set screws. Set screws, which do you think, if I stuck this in a hole, what would locate on the hole more precisely, this or this?
What are you doing?
I want to put a pulley on here. I'm going to put this pulley on this shaft. Now this has no flat and this has a flat. Is there any difference in terms of the precision of the concentricity between the two? There's a huge difference depending on how you do it.
The full circle would be better?
The flat circle would be worse.
Yeah, the full circle.
Yeah, full circle would be better. So we'll give this a check mark. So imagine this wiggles more because you're missing all of this material. Now, you're free to have a theoretical argument with me about geometry, but I can tell you, just having used these repeatedly, this wiggles a hell of a lot more than this one. When you're clamping, you don't want to clamp with anything with a flat or key. You always want to clamp on a full circle. You always want to locate off of a full circle. If you locate off of this, it's going to wiggle a lot more. You're missing that material. It's able to just wiggle as much as it wants there, that way. Uh-huh.
But if you want to dremel a flat on your set screw, why would you dremel the whole shaft? Why won't you just dremel a little piece that will fit there? So you won't have that problem.
You're right. Let me give you another thing. So you're saying don't dremel all the way down, just dremel this a little bit? One reason is you have to put plastic around all this and tape it down. The closer you get here, the less distance you have. What I do, I take compressed air and I blow it on the shaft while I'm doing it. I've also seen people and have done where you take this and then dunk this in water quickly to cool it. And basically you need room to work with here, right? If your bag's right here and you're dremeling right on top of your bag, you're increasing the chances to screw up and get particles in your bearings. So you're right. You could just dremel this little section. It's just more dangerous. So let's go over this again. Configuration upside down or right side up. If I do this way, I have to dremel right next to the bearings, which is dangerous, and my force is higher. And if I didn't dremel just this part, if I dremeled the entire thing, most of the shaft is bad for locating. I only have this itty bitty little section of the shaft that's a full circle for locating. If I turn it upside down, my lever arm is smaller, so I have low radial torques. I only have to dremel a little bit and it's far away from the bearing, so I'm good. And most of the shaft is still full circle for locating precisely. So if you have the choice between the two, always do this one. Does everyone believe me intuitively about the poor locating qualities of the flat? Is that unbelievable, believable? Okay, next we're going to talk about unicorns. Okay, let's look at this. Remember that pesky torque constant? Number 12. Millinewtons per amp. It's not written up here anymore. Tau is KTI. That's KT. It takes amps and converts to torque. And then the speed constant is below it, RPM per volt. Okay, any questions about that? Give me one sec. Okay, cool. I'm going to go through one last thing. This is going to wrap up our DC motor. Let me check. I want to make sure we didn't miss anything important. Does anyone have any questions at all about DC motors right now?
How expensive are Maxon motors?
The RE30 is like 150 or 200. I think some RE50s I just got are like 450. So, but again, you need to keep in mind if your advisor or your employer is unwilling to pay for you to build the robot the right way, then I would prefer to simply say screw it and not build it. I don't want to build things that suck just because someone's cheap. What you need to do is convince them of their cheapness and the futility of building cheap robots and get them to pay for the real stuff. Okay, there's another way of connecting to a motor I'm going to show you, and it's not particularly different, it's a part. Don't open bags with your teeth. I probably just ingested something nasty. These are called motor hubs. Okay. So the shaft of the motor goes in the middle. Okay. And then what's that for?
Set screw.
Set screw. And what are these 4 holes in the face for?
Down and located.
Nope, bolting to whatever you want. Let's look at this one. Now there's a bigger one. This is just another motor hub. And what's the hole for? Set screw. And then these holes are just for bolting to whatever I want. It's just these are pretty cheap. It's like $10 or $5. And it lets you, you could imagine putting a pulley on here. So the shaft would locate the center for concentricity of the pulley, and then the bolt holes would transmit torque.
On the second one, why were there 2 holes for the set screw?
2 holes for the set screw. So 2 instead of 1. You tell me. What do set screws do?
They vibrate loose.
Okay. What are set screws supposed to do? Nope. Fundamentally, why are we using any type of clamp or set screw or anything? To transmit torque. Set screws transmit a finite amount of torque. You can't put an M1.6 or M2 set screw and expect to have infinite torque. There's an equation in any standard machinist handbook, I don't know it offhand because it's long and boring, that based on the diameter of the shaft and the size of the screw, the max torque carrying capacity of that one single set screw. Okay, well, for a given screw size, we have max torque. So now if you want double the torque, you have 2 set screws. Then you have twice the opportunities to get screwed in terms of it vibrating free. Let's see for a sec. There was something interesting here I wanted to tell you about. Yes, Pulley amps. We're going to finish I/O real quick. Does anyone know what an enable line is? Okay, for those of you who don't, the safest way to have a robot is that it can't do jack without you explicitly pressing a button that says you are safe to go ahead and operate. It's called the enable line. This is typically hooked up to a giant red button. When you smash it, it disables the robot. Oftentimes they have 2 separate ones. They have an active enable line and they also have a disable line. So if you're not pressing the enable line, or conversely you're smashing the disable line, everything shuts down. And this isn't in your computer. What happens if, say, we were to read this in to a digital in on our computer, and our computer froze, and our robot was stuck on, and we're smushing the button, and the computer doesn't care because the DAT card froze. Thank you, National Instruments and Linux. Don't read enable lines on digital lines in your computer. These go directly to your motor amp. And they don't go to one that you built. They go to one that you've bought and it's industrial grade, and they tell you, guaranteed, if you press this line, it will stop working. This is a safety thing. And anyone know what limit switches are? Limit switches are directional enable lines. Okay? So let's draw here for a sec. Say I have a rack and pinion. Okay? Here's my little pinion, here's my rack, and I'm going to move back and forth. When I get here, I would like a little switch, okay, to tell it to stop moving, or else I'm going to strip off all my teeth. When I get here, I would like another switch that says stop moving, or I'll strip off all my teeth. These are each called limit switches. On really nice amps such as Copley, you feed this electrical signal into your motor amp. And what happens is it stops moving in that direction only. Okay? So if you hit the right limit switch, it can't move right, but it can still move left. If it hits the left limit switch, it can't move left, but it can still move right. Maxon, yeah?
For the enable line that you were talking about with the button, why would you put it into the motor amp instead of the button, like open up a switch or something?
I would put it into both. For me, I want soft stops and I want holy shit nuclear war stops. The soft stops are my code spazzed, but no one's in danger. So I do IV robotics. So for my robot, you stick your arm in and it pokes you with a needle. If I'm debugging code and there's no patient nearby, I need a soft stop. So my enable line goes to the motor amp, but it doesn't kill power. 30 seconds later, I can unpress it and everything's good. The oh shit button that is directly to cuts power from the wall socket, that's when the dude's arm is in there. And I don't care what's going to happen to the robot. Someone's about to lose a hand, so I'm just going to literally sever power immediately. And so you always, for safety, you always want multiple tiers. So I literally have one that essentially it's a relay, and so it just takes the plug from the wall and yanks it. It's just a solid state relay, or you could even do an electromagnetic one. Then you have an enable line going to your motor amp. That same enable line goes also to a digital in. So if your robot hasn't frozen on the computer, it's a soft stop. It doesn't have to hard reboot the computer. So basically every signal goes everywhere except for the death switch, which is I'm yanking from the wall.
Can I do one follow-up?
Yeah. Mm-hmm.
For your robot in particular, do you have any spring-loaded stuff so that, like if you cut power to the robot, the last thing you want it to do is, under the weight of the arm, shove the needle further into the patient?
Exactly. The answer is yes. And that is about counterbalancing and backdrivability. Counterbalancing is if power goes down, say I have a robot arm and it's wielding a knife, it's a sushi robot. When power shuts down, is it going to go, nyeh? You don't want that. You would like a counterbalance so it just hovers. The other issue is backdrivability, which is if it's right here, it didn't cut me, but I'm a bit uncomfortable with this close of a shave, and I shut down power and it's counterbalanced, can I get it out? Can I push it out, or does someone have to get an Allen key for the set screw that holds the knife? So for any type of safety issues with robots, you want counterbalanced, and you want backdrivable, and you want multiple levels of enable line to the motor amp, death switch to the actually yanking the cord from the wall / solid state relay. Now the limit switches are mainly to prevent destruction of your mechanism. Okay. In Copley, part of the reason why Copley amps are so nice, and we'll let out in 2 minutes, the reason why Copley amps are so nice is they have an enable line and they have a left and right limit switch built in. And you can program them to do whatever you want. They don't have to be enabled, they don't have to be limit switches. They're intended as such, but you can flip the polarity. Maybe 5 volts is on, maybe 5 volts is off. Maxon motor amps only have an enable line. So the only thing you can do is you feed the enable line plus left and right limit switches in OR configuration into the enable line on the Maxon driver. But then it kind of kills your robot, right? Because if anything happens, you're like, oh, well, I'm done. I can't move out of the situation. So then you have to reset the robot. So I keep harping on the Copley amps, not only because they're industrial grade, they don't fail. They have really nice enable line plus left and right limit switches. Plus they give you actual torque commands and current. And if you get the digital ones, you set the transconductance digitally. It's really fast and easy. That concludes DC motors. Now just real quick, on Wednesday we're going to talk about how do you measure things precisely. If there's one lecture you should not miss all quarter, it is on Wednesday. Because I notice a lot of people don't know how to use calipers properly, which means all of your measurements are wrong. And well, she's not here, but at any rate, if you want to play the trick of measuring the right shaft, you don't have to sand it. I saw some people using calipers. You don't want calipers for that, you want micrometers, and I'll show you how to use those on Wednesday. And we have them in the tool chest, but no one's been using these wonderful, beautiful tools because they don't know how to use them. So Wednesday we'll be talking about measuring, and then after that we'll be talking about springs. We're good.